Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss how not to cheat. So, in this lesson, we will describe the question on the final examination that was the source of most cheating. We will look at a correct solution, or at least the solution we expected students at the first year level to achieve. And a number of students did get this solution. We will also review how Marmoset keeps all submissions, not just your most recent or the one with the highest grade. We will then describe how students failed at this particular question by plagiarizing a solution from an online solution that first does not solve the same problem we posed on the examination, but not only that, has a bug in it so that it doesn't even solve the problem it claims to solve. So to begin, how not to cheat. Don't cheat. If you cheat, you have to be smart enough so as to be able to solve the problem without cheating. So don't cheat. Some students did not even attempt the problem. They got 0. A student who cheats should get a lower grade than one that did not try the problem. The question was straightforward. We defined a saddle point as a point in the matrix being an entry such that it is strictly less than any other entry in the given row and strictly greater than any other entry in the given column. It's important to note that we did not define a saddle point as any point or entry in the matrix that is less than or equal to any entry in the given row and greater than or equal to any entry in the given column. Now, because it was an m by n matrix, we thought we'd make it easier by simply having the matrix indices go from 1 to m or n respectively, so as to make the code more similar to what students had already seen in their linear algebra course. We even gave them a loop that prints the matrix entries. As you will note here, there's no requirement to understand what a two-dimensional array in C++ is. We simply have a matrix object and we can access the ijth entry by using parentheses. Note that we gave them 2 for loops that go from 1 to the row dimension and from 1 to the column dimension. We also gave the students a matrix that clearly has floating point numbers. As you can see, we indicated that yes, this matrix does have a saddle point specifically at entry 4,1. You will notice that 23.96 is strictly greater than all other entries in that column and strictly less than all entries in that row. We also gave them the declaration of the indexing or parentheses operator, and this is clearly defined to return a double. Now, how do you solve this problem? Well, all you really have to do is take our code that goes through all of the entries of the array or the matrix anyway, and check if Aij is a saddle point. And if it is, return true. Otherwise, if we've checked every entry in the matrix and it is not a set and no points are saddle points, we return false. So what were we looking for? Well, we would nominally expect students perhaps to consider having a local variable isSaddle, which is initialized to the value true. Then we expect them to check to make sure that Aij is strictly greater than all other entries in that particular column. So we check all entries in that column, and if Aij is less than or equal to any other entry in that column, we set isSaddle to false. Similarly, we must ensure that Aij is strictly less than all other entries in a particular row. So again, we check all other entries in that row to see if Aij is less than or equal to that other entry, in which case, once again, we set isSaddle to false. Having compared the entry Aij to all other entries in the row and column in which it is contained, if isSaddle is still set to true, we return true. Now, some students, even with a very limited amount of time on the exam, tried to optimize this by breaking as soon as isSaddle is set to false and only running the second loop if isSaddle is still true after checking that column above. Similarly, we break early if we determine that it is not a saddle point. This was not required, but 1 or 2 students actually went to this extreme. If you were one of those, nicely done. Consequently, if you take a look at our solution, however, notice that we provide approximately 50% of the characters required, because all you now need are 2 additional for loops that go through the rows and columns of the entry Aij. Unfortunately, we did call it a saddle point, and so many students, almost 100, broke the rules of the examination and looked up the solution online. A Google search for saddle point C++ yields as the first site this particular solution on Geeks for Geeks. There were, however, a few problems with this online code. It had comments that probably should not have been copied over. It uses a 2-dimensional array data structure and not our matrix class. So for a 2-dimensional array, the indices go from 0 to m-1 or n-1 respectively. It was a 2-dimensional array of integers, or int, not a 2-dimensional array of double. It was a square matrix. The problem solved was the standard definition of a saddle point. That is, an entry of a matrix that is less than or equal to any entry in the given row and greater than or equal to any entry in the given column. Less than or equal to, greater than, or equal to. Also, the solution we expected does not have an exceptionally great runtime. The runtime is big O of m times n times m plus n, which is big O of m times n squared plus m squared times n. Now, students in the class do not understand analysis such as this, because that is covered in a subsequent class. However, the online code actually attempted to optimize the solution by first finding the smallest entry in a given row, and then checking if it is the largest entry in the corresponding column. This is a much more efficient runtime. So for a square matrix, the runtime is order n squared. However, for a non-square matrix, the runtime is order mn, which is still much more efficient than the default solution we were looking for. But again, the question did not ask anyone to optimize the problem. And given that students are writing these solutions during an examination, it's very unlikely that a student would be, coming up with an optimal solution. So again, it's important. We were not asking students to optimize anything in this final examination. No runtime requirements were even hinted at in the question. So it makes one wonder why students would be submitting solutions that are, or at least appear to be, optimized. However, this is not the most significant problem, however, for the solution online has a serious bug in it. It finds the first smallest entry of a row. Oh, wait a second, a row may have 2 or 3 small entries, and only one of them may be a saddle point. It only checks if this first smallest entry is a saddle point by checking that it is the largest entry in the corresponding column. So, if there were multiple entries in the first row that had the smallest value, it would not check the subsequent smallest entries and therefore could potentially miss a saddle point. Thus, in theory at least, all students who approach the problem in the manner presented online are almost certainly guilty of copying the code. There was no reason to try to optimize the solution. The description of the problem actually gives a very clear strategy for solving the problem, even if it is inefficient. And no hint anywhere was given that we were looking for an efficient solution. However, that's not the only problem. Because remember, a student who is already copying is probably suboptimal. Therefore, they're going to make other mistakes. Most students who copied verbatim or strongly paraphrased the comments appearing in the original source code online. They did not try to understand how the online solution was solving the problem at hand and therefore did not try to make any significant changes. They kept the same variable names and the same declarations. The variable storing the value at the minimum entry is declared to be of type int, or even of type standard size t instead of double, because after all, the online solution has an integer array and not a matrix that stores double precision floating point numbers. All the variable names are either the same or very similar to the online version. On occasion, some students actually tried to change the names of the variables from that on the online version. They still had the loops running from 0 to n minus 1 instead of 1 to n, even though we explicitly gave them for loops that showed and that these matrices were indexed from 1 to n. They also accessed the first or stored the first entry as AI0 and not AI1. Here are some examples. In the online code, we have this: declaration and initialization, using, of course, declarations and initializations from previous versions of C, not C++11, which is what we taught in this course. Here we have one genius who was smart enough to replace the access to matrix entry I0 with the matrix entry I1. Notice, however, though, that even though this is returning a double, the local variable minrow is nevertheless still of type int. Column index is also initialized to 1 as per normal. Other students changed int to standard size t, not double, but standard size t. Here's one brilliant student who was smart enough to change int to double, but is still accessing the matrix as if it was a two-dimensional array. This student was clever enough to change the name of column index to column index min. But again, clear evidence of plagiarism. Another student included this interesting comment. Now, why you're commenting on a final examination where we are simply testing you in Marmoset is beyond me. But in the online code, we have the comment, oh, find the minimum element in row or of row I and column index of minimum element. Oh, nicely paraphrased. That could have been a coincidence, but the next comment is, oh, check if the minimum element in the row is also maximum in column. Check if the minimum element of row is also the maximum element of column or not. Also, there were lots of other comments that were repeated. One student included a cout statement verbatim from the online source code. Thank you. And many other students included this exact same statement where the only variation was small changes to the text or small changes to the variable name, such as instead of min row, we had row min, and instead or mr, or some other variation. Now, this is only the most egregious, and in most, well, actually in all cases, there were numerous indicators of plagiarism, more than enough to determine guilt beyond reasonable doubt. There were more subtle indicators as well. For example, if you wanted to correctly update the code, this particular for loop should start at 2, not at 1. The online code itself is horribly written as well. Here we're missing some parentheses, so it's not really clear, apart from indentation, where the loop and conditional bodies are, and students had issues with attempting to put the braces in the correct locations. There were many modifications to this piece of code, but all in all, again, it was almost all very similar. Again, some students were also very kind and kept the comments. Now also, we don't only look at your final solution. Please remember, we have copies of all of your submissions to Marmoset. So for some students, it's rather interesting and actually sort of fascinating to see how in subsequent submissions to Marmoset, the solution that is submitted slowly diverges from the one that is cut and pasted from the web in order so that it changes so it actually solves, or at least attempts to get closer to solving the problem as posed on the final examination. But of course, there are so many fundamental problems and differences that it doesn't seem that this happened all that often, and I very much doubt it did at all. In one case, the student was well on the student's way to coming up with a correct solution. And then the very next submission on Marmoset, we see that it's clearly copied from the online version and then begins to diverge from there. That student could have gotten 0. Instead, now the student will get 0 on the entire examination. Now, as prescribed by the University Secretariat, premeditated academic misconduct on a final examination requires a 0 in the examination, failing the course, and a suspension. Opening a browser and doing a Google search is not an opportunistic attempt at academic misconduct. It requires that the user deliberately open a browser and deliberately enter what is being searched for, and then explicitly copying and pasting that solution. Please remember also that any form of misrepresentation is also an academic offense. If you claim that you did not copy the solution from the web, or copy it from another student who copied it from the web, and we prove beyond reasonable doubt otherwise, we will ask for an additional penalty on top of any penalty you receive for plagiarism on the final examination. The sad truth is that because of COVID-19, the final examination only counted for 30% of the final grade and not 50%. So a good portion of the students who cheated already passed the course. Almost all the students who cheated would have passed the course with as little as 33% on the final examination. But that was not enough. In this topic, we've covered the question that saw the greatest amount of plagiarism on the ECE 150 final examination, and what students were doing when they were foolish enough to attempt to cut and paste code from the web. We offer a sincere thank you to all of you who did not copy the code from online, even if you left that question blank and consequently did get 0. Here's our one reference, acknowledgements, colophon, and a disclaimer. Cheers!